Welcome to our first lesson on exponents and scientific notation. This is section 1.2 in the textbook. So let's jump right in. We have some learning targets for you to begin. And I'm going to start with just reminding you of some exponent rules that you may already know about. The first is the product rule of exponents. And the product rule basically says that if we have something that has the same base and different exponents and we're multiplying those together, we keep the base and we add the exponents. In a similar way, if we have the same base and we are dividing two numbers with the same base, then what we're going to do is keep whatever that base is and we subtract the exponents. So I think most of you are probably familiar with this. I just thought I would review that quickly. And then here are a couple of example problems. If we have k to the 6th times k to the 9th, we can use that product rule, and that just says we add the exponents to give us k to the 15th. The second example here, our base is 2 over y, and the thing to remember on this one, if there's no exponent, it's assumed to be 1. So this is really like having a 1 up here when there's nothing there. So 2 over y to the 4th times 2 over y to the 1st gives us 2 over y to the 4 plus 1, which is 2 over y to the 5th. And we'll learn how to simplify this even more in the future here, in this lesson. Letter C, we have the base t, and we want to add all those exponents, giving us t to the 14th. All right, here are a couple more examples. This one uses that division rule or the quotient rule. So letter A, we have s to the 75 minus 68, giving us s to the 7th. Letter B, we have negative 3 to the 6th, and then negative 3 to the 1 on the bottom, and we subtract, so it's negative 3 to the 6 minus 1, which is negative 3 to the 5th. And again, we'll be simplifying these further later in the lesson. And then letter C, our base is e f to the 2nd. So we're going to keep that base and we're going to subtract the exponents. 5 minus 3 gives us f squared to the 2nd power. All right, so here we go playing by the rules. I have a list of rules for you here. The power rule, the zero exponent rule, negative rule, power of a product, and power of a quotient. So the power rule of exponent says if you have a base and it's raised to an exponent, and this stuff inside parentheses is raised to another exponent, well, that is basically our repeated multiplication, so we're going to multiply our exponents. So it's a to the m times n. Now the thing to remember is everything in the parentheses gets raised to that n power. So if you have constants in here, they also get raised to the n power. The zero exponent rule of exponents says that any number that you have, as long as it's a real number, anything to the 0 power is 1. The negative rule of exponents says that you have something to a negative exponent. That's the same as the reciprocal of that thing to the positive exponent. So the negative exponent rule just gives us a reciprocal to the positive exponent. And the power of a product rule says if we have some stuff inside parentheses raised to an exponent, everything in the parentheses gets raised to that exponent. And the power of a quotient is very similar to the power of a product. Again, everything in the parentheses gets raised to that exponent, and you still end up having your quotient. So let's put these into practice and take a look at some examples. So in this example, we have 3y raised to the 8th power, and then that whole thing raised to the 3rd power. Well, we could say that that is really 3y to the 8 times 3, or 3y to the 24th. Letter B, we're going to multiply 5 and 7 and get t to the 35th. And letter G, we're going to get negative g, and we're going to just multiply these together and get negative g to the 16th. Okay, now these are not simplified all the way. This is just using the rules that I've introduced so far. Letter D, t to the 7th over t to the 7th, that gives us t to the 7 minus 7, which is t to the 0, so that's our 0 power rule, and anything to the 0 power is 1. Letter E, we could easily, on letter E, we could just cross these two off, because anything over itself is 1. And if we do that, we are left with 1/2. That's one way of thinking of that. The other way to think of that is it's DE squared to the 11 minus 11, which would be 0. So this would give us a 1 anyway, no matter how you look at that. Letter F, again, we're going to add the exponent. So we have t to the minus 5 power. Well, now our negative exponent rule says anything to the negative exponent is equal to the reciprocal of that thing to the positive exponent. So we have 1 over t to the 5th. And letter G, we're going to subtract those exponents, so we get 25 to the negative 1. But then our negative exponent rule says that's really the reciprocal of 25, which is 1 over 25. All right, moving right along. Letter H, another example for us. This one, everything inside the parentheses gets raised to that third power. So we have negative 3 to the third power, and then y to the 5th raised to the third power. Well, we know we multiply these, so we get y to the 15th. And then we can simplify negative 3 to the third. Remember, a negative number to an odd power will always be negative. A negative number to an even power will be positive. So when we take 3 to the third power, we get a 27, and because it's an odd power, we get a negative 27. So this is our final answer. Letter I. This one we're going to multiply everything in the parentheses. Their exponents will be multiplied, so I get 1 over a to the 18th, b to the 21st. Letter J, again, we're multiplying a power to a power, so we get r to the 12th, s to the minus 8. But that negative exponent, we're going to use that negative exponent rule, so that tells us it'll go to the opposite place. This will go to the denominator and become positive. So we get r to the 12th over s to the 8th. And then letter K, 5 to the 4th over u to the 32. Well, 5 to the 4th can be simplified, and that gives us 625 over u to the 32. Letter L, negative 1, because it's a negative number to an odd power, is going to be a negative 1. And then w to the 3 times 35, which is 105. Here are some more examples where we're going to be simplifying expressions, and in this one it says you're not allowed to have any negative exponents, only positive exponents. So here we go, 2 to the negative 3, u to the negative 3, and v to the positive 6 just by multiplying our exponents. But now we've got to get rid of these negative exponents. So v to the 6th will stay where it is, u to the minus 3 is going to go in the denominator, and so is 2 to the negative 3. When we simplify that, we get v to the 6th over 8 u to the 3rd. Remember, 2 to the 3rd is 8. Because it's negative, it goes to the denominator. Letter B, we end up adding all of those, 8 minus 12 plus 1. So that gives us a final answer of x to the minus 3, which is equal to the reciprocal of 1 over x to the positive 3. Letter C, everything in the parentheses gets raised to the second power. So we end up getting e to the 4th, f to the negative 6, over f to the minus 2. Cleaning up our negative exponents, okay, the negative f to the minus 2 will go up, f to the minus 6 will come down. So we will have a net change. We have e to the 4th stays where it is, and we end up with 4 f's on the bottom. So that is our final simplified answer with positive exponents. Letter D, multiplying these together, we're going to use our commutative property and rearrange some things. Multiplying 9 and 3 together, r to the minus 5 times r to the 6. Remember, we add the exponents. That'll give us r to the 1st. S to the 3 minus 4 is s to the minus 1. So we need to multiply our 9 and our 3, and we need to make the s to the minus 1 go to the denominator, giving us 27r over s. Almost to the end here. Scientific notation is the last concept in this section. And a number's in scientific notation when you have a number part times a power of 10. And the number part, the thing to remember here is that is a number that's bigger than 1 but less than 10. And it has to be a positive number, okay? The absolute value of that thing is greater than or equal to 1 but less than 10. So it's an integer. So I misstated that. It's not a positive number. It just means that this number is greater than 1 but less than 10. It could be a negative number or a positive number. So here we have a couple of examples writing the numbers in scientific notation. The U.S. national debt per taxpayer. Well, what we need to do to write this in scientific notation is we need to move our number to be between 1 and 10. So the only place to put that decimal place where it's between 1 and 10 is right between the 1 and the 5. Now, without doing anything, it's assumed to be at the end of the zeros. So how many places did we go? We went 1, 2, 3, 4, 5 places is what we've moved. So we've changed our decimal 5 places. And the rule I like to use, if the number you're starting with is bigger than 1, then your exponent's going to be positive. If the number you're starting with is a decimal value less than 1, like letter E down here, then that will have a negative exponent. So this should be 1.52 times 10 to the 5th. Now remember, you should always list all of the digits, all of the significant figures that you have in the problem. Since we have a 5 and a 2, we have to list those. We don't want to cut off any numbers. The zeros are okay to cut off because those are represented in the factors of 10. World population, okay, if we have a decimal point at the end of the zeros, we're going to go 3, 6, 9 places to put it between the 7 and the 1. So we get 7.158 times 10 to the 9th. Letter C, we go 3, 6, 9, 12, 13 places. Whoops, I have an error there. Should be 8.55 times 10 to the 13th. So ignore that decimal point. That should go, I'll just correct that really quickly, 8.55, not right there, okay, 8.55 times 10 to the 13th. And letter D, we're going to put our decimal point right between the 3 and between the two 3's actually, right here, 3.34. Okay, that's the number that will be between 1 and 10. And so that tells us we've moved our decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9 places. And because this number is less than 1, it's 10 to the negative 9. Last problem, the decimal point will go between the 7 and the 1. So we get 7.15 times 10 to the minus 8. So, last slide here. Converting numbers in scientific notation to standard notation. If it's a positive exponent, you go to the right. Negative exponents go to the left. So just moving those decimal places, we get those answers. All right. And performing the operations, write the answer in scientific notation. So what you're going to do here is you're going to multiply the number parts together, and then you're going to add the exponents for the powers of 10. So you're going to have 10 to the positive 6. But then you may have to adjust if your number's not in scientific notation. You need to do that. And this one, it actually turns out to be in scientific notation. I need to add one little thing here. When we're multiplying a negative times a positive, we need a negative in there, right? So it's negative 8.475 times 10 to the 6th. And then example B, 1.24 multiplied by 1.55. And then our powers of 10 would be 10 to the positive 29. So we get 1.922 times 10 to the 29th. All right, our last example here, word problem. An average human body contains around that many red blood cells, and each cell measures that many meters long. Write the numbers in scientific notation and the total length if the cells were laid end to end. Write the answer in both scientific and standard notations. So if we go ahead and write our first numbers in scientific notation, we get 3 times 10 to the 13th. This one gives us 8 times 10 to the minus 6. When we add our exponents, 13 minus 6 is 7, but when we multiply 8 times 3, we get 24. So we needed to move that one place to the left, which made the number smaller, so we have to increase our exponent by 1. So 2.4 times 10 to the 8th. And then writing that in standard notation, we're going to get 2, 4. So that moved at one place. We've got 7 more to go. So that's how many zeros we need to add. 1, 2, 3, 4, 5, 6, 7. So that would be our standard notation, and it helps to put your commas in there after every 3 sets of 0. That's it for this video. We'll see you next time.